The nice part about attosecond physics is that you're doing really fundamental physics, right? You're trying to learn what electrons do, like how they move, what predicts what they can do in a solid. On the other hand, these are very pressing questions for technology. Hi, I'm Marcus Ossiander. I'm assistant professor for physics at the University of Technology in Graz. I'm working on metasurfaces for ultraviolet radiation. And I was part of IMPRS during my PhD from 2014 to 2018, which I did at the Max Planck Institute of Quantum Optics. So I have a PhD in attosecond science, and attosecond science is very closely related to having extreme ultraviolet radiation because we need this very fast oscillating radiation to make short pulses. But there's almost no way to manipulate light in these frequencies, and that's a huge problem both for technology and physics. And now I'm developing optics for this weird spectral region using a very novel technique. It's called metasurfaces. Metasurfaces or metaoptics, it has this word meta, and it technically stands for an optic that's made out of many, many small optics. So what we do is we put many nanostructures on a flat piece of substrate, and the combination of all these many millions of nanostructures then forms a large optic. What every single of these small nanostructures does, it manipulates the phase of the light that passes through it, and that allows us to make really fancy optics. So metasurfaces, they have multiple aspects of why they're important. In the visible regime, they give us more freedom to design light, because usually you're limited to the shapes that you can grind glass, and you can maybe grind a lens or a little bit of a aspherical lens, but you cannot grind arbitrary shapes. Now with nanostructures, we can make arbitrary phase profiles, and that allows us to manipulate light on a much smaller scale and with much more freedom. In the extreme UV, there's a different aspect because we have no materials that transmit extreme UV. So we cannot make a lens for extreme UV just because all the light is absorbed. And metaoptics have a property that they are very, very flat. And because they're so flat, even though we make them out of absorbing materials, some light makes it through. And now we can make transmissive optics. So it's the only technology that can make transmissive optics in the extreme UV. That's why they're important to us. So what I'm really finally interested in is solid state physics. But not only the physics of a huge piece, but also a small device. And these devices, like transistors in a processor or, I don't know, switches, they get smaller and smaller. So we have to be able to look at really tiny structures and to concentrate a lot of light on them. And then we also want good time resolution. So we want the attosecond pulses. Now, that means we have to build a microscope that can see tiny structures, but also preserve time resolution. And that's what we think we can do with these metasurfaces. So we really use them as a tool to maybe make a microscope and then look at these really small solid-state devices with super good time resolution, and then learn what the electrons are doing in the first couple of femtoseconds after you excite them. The nice part about attosecond physics is that you're doing really fundamental physics, right? You're trying to learn what electrons do, like how they move, what predicts what they can do in a solid. On the other hand, these are very pressing questions for technology because we make these tiny switches, we use them in our phones every day, we want to make them better. We make solar cells, and it's really important if a solar cell works or not is defined in a very few femtoseconds, if it's efficient or not. And these are questions that we have some idea of what's important, but we cannot yet observe these processes really, and we get to examine if we can in the future, or make the tools to observe them in the future. So we think, even though we do this super fundamental stuff, we can have some influence on technology, which is nice. Oh, my typical day. So I think during my PhD, it was mainly lab work. We built the experiments, or we ran the experiments, and then we took some data, and then we did the evaluation, but you were super close to the experiment. Everything you did was the experiment. And then as you progress, you get teaching, which is really nice, and it starts to take some time, but it's also really rewarding. It's super fun. And as you progress more, you also get a lot of administration and grant writing. So now I guess my typical day is I come, I do some emails, I try to do an hour or two of research, then I do some teaching usually, or I prepare for a lecture, depending on if you're trying to apply for money or not. I spend 2 or 3 hours writing a grant, and then I try in the evening to do some more like data analysis or more experiments sometimes. The cool part of the program is that there is a cohort of people. So you get to meet people working in the same field, but on very different topics, doing theory, doing experiments, and getting to meet all those people and hear about their experiments and try to understand what they're interested in is a really cool part. And you get to go to Ringberg once a year and like talk about science. It's nice. So I think the best part about science is that to get to talk to all the people, right? So my advice would be that everybody is happy to talk about their science. So approach everybody that you can find and ask them about their science. Because from the grad student to the prof, everybody will be happy to tell them what interests them and why they're looking into it and how they're looking into it. And you can learn so much from these conversations, much more than you could learn from like reading papers all day, because they will like be super concise and give you a really nice picture. So just approach everybody and ask them about their science.